Hi, I'm Bianca. I'll be presenting to you about my project, Spectrometry with Michelson Interferometer. So, what's a Michelson interferometer? Basically, you split a single light beam into two, reflecting both light beams and recombining them such that they interfere with each other to create bright and dark fringes. These fringes shift when you vary the optical path difference between the two light beams as a function of the light's wavelength. This means that if you measure the intensity of the fringes at a fixed point, you are able to determine the light's wavelength. By Fourier transforming the data, you can determine the spectral line width of the input light. In other words, you can determine how monochromatic the input light is. So we put these ideas together to build a spectrometer that can determine the spectral line width of the laser light, as well as work with low intensity light. We use 3 Hini lasers of wavelengths 632.8 nanometers, splitting each beam with a cubic beam splitter. We then shifted one of the mirrors by mounting it on a linear motor with a precision of 15 nanometers. We used a self-assembled avalanche photon detector to measure the fringe intensities over 1 minute for each laser at each data point. In order to find the wavelength, we attempted to best fit a sinusoidal function onto the resultant graph of intensity against optical path difference. However, we are unable to find a convincing best fit due to severe overfitting. We then Fourier transformed the data to obtain the spectral line width of the laser by measuring the full width at half maximum of the graph. We then compared these measurements to those of a commercial spectrometer by Ocean Optics. We were also able to work with light of low intensity by dimming the laser light with pairs of linear polarizers due to the sensitivity of the avalanche photon detectors. However, the precision at which we found our spectral line width was much lower than that of the commercial spectrometer, as ours was on the order of 40 to 60 nanometers for the full width at half maximum, while the commercial spectrometers was on the order of 1 to 2 nanometers. Overall, we succeeded in building a spectrometer that was able to work in low light intensity and also find the most monochromatic laser. Further work can be put into refining the physical stability of the setup, as that was a major contributing factor in why we found difficulty in determining the wavelength of the laser light by best fitting the resultant graph. As we only work with laser light of one wavelength, we could also extend our project to work with different levels of intensity, as well as different wavelength ranges apart from the visible range. We could also modify our setup to work with other types of light apart from collimated laser light, such as thermal light. For more information, you can check out my poster in the link below. Thank you.